Okay, so thank you everyone for having me. You can see my slides. Okay. All right, great. Thank you again to the organizers, the volunteer team, Patrick, everybody. I'm thrilled to be here alongside Professor Kovac and all the distinguished guests here. And I'm super excited to see all of the videos and notes, especially from the times when I was asleep. But I am a new assistant professor as of this year at Western Washington University. So I'm here in part to pitch my new lab. We are doing robotics for the planet. I'm hosted within the computer science department. I've traveled between physics and electrical engineering and computer science, and now I'm at home in computer science with algorithms and things like that. We've got an amazing lab that has been built by some very generous donors. We've got a good, solid undergraduate program with majors in computer science, data science, and cybersecurity. We've got a healthy graduate student population. We're a master's granting institution, so I'm in a sort of lucky spot where I don't have a full lab of PhD students to support, but we still have access to some really top-notch students who are doing research. And our new building is amazing. It's energy efficient, won sort of awards, and we share that with electrical engineering and energy systems, which is great for the kinds of topics we'll be talking about at this conference. And most importantly, our lab has windows. After a career of working in labs without any windows or access to natural light, this is our view. Some new trees we've planted to our arboretum that Western co-manages. It's just a natural wooded area with native plants and things like that. Of course, Bellingham is located on Bellingham Bay on the Salish Sea on the Pacific Ocean. So we are very aware of our place in the world and our place in the water cycle and all of those good things. It's a wonderful place to visit too. So if you're ever in Vancouver or Seattle, please contact me. We'd love to have folks up for talks. So I'm here sort of as an emissary from theoretical robotics, which is an analog to theoretical computer science. It's been going since the 90s, maybe earlier. In the sort of thrust of it is to identify trade-offs and orderings in robot systems that we can understand and formalize. Anyone who's built robotics probably understands this intuitively, but there's different trade-offs. So we could have a robot with one very fancy sensor that's expensive, and that might act very similarly to a robot with a cheaper sensor that we've done some very intelligent recalibration and auto-calibration procedures with. Similarly, we could have multiple robot systems that are able to cover the same area while moving more slowly as one robot that's moving very quickly. So there have been various efforts to formalize these realizations, to automate the system design process, to prove things about system design performance, limits, are there minimal resource requirements for certain tasks, all of that good stuff. And of course, robustness and safety is a big part of that. It's a challenging problem, right? Because it's a huge multi-dimensional design space. We have all these resources such as runtime. How does that scale to real world environments? How much space do we need on board to store all this data? How much energy are we actually consuming? What sort of actuators do we have? How expensive are they? How energy efficient are they? We also have this design space over sensors, so resolution, calibration, all these questions. Communication networks, are all of your robots decentralized, centralized? What sort of communication protocol and underlying medium are we using? And of course, maybe things like supply chain. So if there was something wild like a trade war going on, you would still be able to build your robots. So we're interested in this very big problem. There's no way to maybe optimally solve it with one single magical tool. So we build lots of tools, and especially interactive tools that help us explore this design space. And I've just highlighted this work on mapping elites by other folks, which is a great idea of the same sort of paradigm. And I don't have time to go into all of the history of this area, but here's just a random sample of related works if you're interested more on the theory side. So my background is in motion planning. working with some experts in motion planning, but specifically on the problem of contact-aware robots. So I used the Roomba model for most of my PhD. We're looking at robots that can, like the one that Professor Kovac just showed, actually make contact with the environment and even gather information from that, and maybe even extend that to manipulating objects in the environment through pushing. So this was super interesting, and we found a lot of promising results that we can actually gain information from the environment and use it to reduce uncertainty in our systems as they're progressing through the environment. But it's, of course, all two-dimensional, very theoretical, far from the real world. So as I became more interested in practical work in field robotics, I began to think about how to proceed with this in mind. And so my realization, or my claim here, to roboticists especially, who tend to frame everything in terms of structured or unstructured environments, usually meaning indoor versus outdoor, my consideration here is that most unstructured environments are actually kind of structured, mostly pretty structured, and we can see that from all the biological systems that have evolved to take advantage of the structure that is there. So my thesis for our lab is that instead of building robots that can sort of overpower the environment, geometry and dynamics, wind, all these sort of things, can we use these forces to reduce system resource requirements while not giving up robustness and performance, which is the real challenge. I'm inspired by systems such as the Global Drifter Array. So we've got over 1,000 buoys drifting around collecting information with essentially no external power. They just have a small solar panel, and otherwise they're driven by the exact currents they're trying to measure. So we're being quite clever there. And can we extend this to more robotic systems? Of course, isn't there some sort of intrinsic trade-off here? Aren't we giving up functionality? I will argue not necessarily, and I'll show some examples here in a moment. And I would push back against this myth of sort of a general purpose robot that can go everywhere and do everything, especially when it comes to affecting the environment physically. And we can see this with our current tools. We don't have sort of a general house cleaning robot. We have specialized robots for specific tasks like vacuuming or washing dishes that are much more efficient than a single robot that could do everything. So lots of examples of minimalism being actually useful in the literature, starting back in the early 2000s, possibly much earlier, but with embodied intelligence, such as the Rex robots that use WEGs, of course, our favorite wheels plus legs, extremely robust in natural environments. And there's been lots of things building on this and even using them as sensors to detect properties of the environment itself. There are, whoops, sorry, I skipped a few slides. Here we go. This is work from my postdoc with Kirsten Peterson at Cornell, where we also looked at a lot of cool construction problems. So I was super excited about Dr. Kovac's slides. But this is a particular project where we're working with soft robots, which I'm super interested in because, of course, we can make them out of more biodegradable materials. And if we wrap our robots in silicon, they're much more, or similar biodegradable materials, they're more robust to environment, dirt, water, things like that. So we were investigating, can we use embedded biodegradable sensors to coordinate multiple modules and have sort of a decentralized coordination scheme? This is, of course, very abstract, but the real important thing is we're able to use these very noisy, very uncalibrated, non-uniform sensors to get useful information out of a system like this. So then we extended some of those insights to multi-agent systems, which my video is not going to play here, but I do recommend you look up our paper at Distributed Autonomous Robotic Systems Conference. We investigated a very old idea about reactive embodied robotics and showed that you can have quite robust collective behaviors as a result for that. So very old ideas around swarming, but in this frame of embodied intelligence and no onboard state estimation, right? Zero onboard state estimation. So we're able to actually bypass a lot of communication, explicit communication through these last two projects, which is huge when it comes to scaling up to large collectives, as well as operating in challenging environments where we might not have access to the same communication technologies as we're used to in cities and places like that. So last example is from my PhD advisor, an algorithm developed there that's gotten some attention, but in my opinion, not enough. It's a very clever data structure based on gaps, so discontinuities in the depth field visible to a robot, and you're able to translate these discontinuities into a discrete representation of the environment that is extremely compact representationally and optimal in terms of distance navigation. So I'm super excited. And the thing about this algorithm is it works better in crowded, cluttered environments like forests or farms, things like that. So I'm very interested in using this for scalable navigation on low resource systems, such as some of the drones that Dr. Kovac was showing, tiny drones. So our lab is going to be focusing in ground-based infrastructure. We're going to be focusing underwater and in forests. So these are challenging environments, but they do have quite a lot of structure, especially the eelgrass forests, in particular for underwater. And we're interested in performance at scale and over long durations, as well as DIY solutions that can be shared easily and replicated in many different places. So our lab focuses a lot on process over results, as I'm trying to really train designers and engineers. So we can place them in all of these wonderful startups and companies that are here. So I'm giving my students solid foundations in these algorithms and representations and math. I think that's very important, but we're also doing embodied design activities. This embodied AI is very, very hot right now. So we've been on that for quite a while. We're doing place-based design, doing movement observation and environment observation. Turns out engineers are typically very bad at understanding what their bodies are doing and what the natural world is doing. So we're learning a lot there, exploring rapid prototyping, fast to fail, fast to try sort of techniques, and of course, open sourcing as much as we can and contributing back to the ecosystem to make better computer-aided design tools for the robot design process, especially in these contextual situations. So super excited for next steps. Unfortunately, we don't have any publications out quite yet. It's been about 9 months. So very soon we'll be sharing some things. We're working on infrastructure. So we're hacking on some power wheelchairs, and Washington just passed right to repair. So I'm very excited to be working on that and mapping sidewalks across the state. We'll also be working with the Sea Discovery Center, which is a very nice seawater-fed aquarium that Western Washington co-manages. So we'll be helping them maintain their tanks so they don't have to go in person and dive into the cold Pacific water to clean up the tanks. And of course, we'll be working with micro-aerial autonomy, especially in unstructured, less structured environments. So I think I'll wrap up there, and please reach out and connect if you're curious about anything I've mentioned, and I'm happy to have a short discussion. Thank you.
Brilliant. Thank you both very, very much, Professor Kovac and Niles, and sincerest apologies, Professor Kovac. I think there was a loss in translation on our side. I think you were communicated 30 minutes and 15 minutes at different times. So sincerest apologies. Thank you for fitting it all in. Nevertheless, really, really appreciate that. Also wanted to share that we've had now 402 registered participants, and they will be getting your keynote videos, as well as the broader public as we share these videos more broadly. So we have a handful of questions, and we'll take maybe about never enough time, right? About 5 minutes. Maybe to start with Professor Kovac, we have a question from Marut, who's a research scholar in India. Could you highlight what sort of tactile sensor array is being used in these small robots, and how you're integrating aerodynamics in the design under, for example, turbulent conditions?
Very good question. Thank you so much. We use some soft tentacles that have embodied sensors in the structure. So typically, we want to use something that's compliant, and where the compliance can be used as a sensor. So it can be used through the structure of the material, or it can be with embedded sensors that are just deflection sensors. The aerodynamics, of course, is an important area. One thing that can help in that is to use neural networks to do the flight control. And as there are more turbulence, and we can use different depths of neural networks. So we had one paper where we showed that deep neural networks are better for flying in turbulent conditions, and more shallow, low computational cost neural networks are better for normal conditions. So I think by having variable depth neural networks that adaptively do that, depending on the condition, I think we have something that is more energy efficient and still high performance. So that would be my recommendation.
Super, thank you very, very much. Professor Nilles, we've got a question. How do you think the lessons and principles from minimalist robotics can be used in modern robotics applications within industry?
Yes, that's a great question. I think the design principles are the most useful thing. It's just a lens where you're considering what is my actual task that I'm trying to complete and what are the resources that I actually need to do that robustly, along with very deep principles like backchaining and fine motion planning, which has really translated into funnel-based control for noisier systems, which I think has been extremely useful in a lot of practical applications. There's more I could go on, but
I'm sure there is. Thank you. Thanks so much. I know we're running up at the time. There's some more questions I want to ask, but maybe, do you have any questions for each other? I don't know how, if you had the opportunity of speaking with each other. So maybe this is also no pressure. If there are no questions, of course, you could always take it offline, but I thought I'd at least create the space.
yeah, that's great. Mirka, I'm curious if you've considered other types of multimodal robots. One thing that we're looking into now is these robots, drones that can roll as well as fly, and that considerably improves energy efficiency. Curious your thoughts on that design.
No, I think multimodal drones or robots can be very helpful. One example that we had is sailing robots that can fly, land on the water, then reconfigure into sailing vehicles and sail on the water surface, measure biodiversity, and then fly off again. So this, I think, is one example, but I think the community is really working on that, and I think it's a very interesting theme. So you're interested in that too? You work on this? Mm-hmm.
Yeah, I'm interested from both the motion planning side, how to plan for robots that can switch modes and then possibly be affected by different environmental forces is mostly my area of interest, but also on the practical side, it just seems very practical.
Makes sense, because often the environment is not predictable, right? You don't know if there's water, there are caves, there are trees that change, the forest is unpredictable, unknown. So having multimodality really helps. Many animals have it too.
Super. I think that maybe we'll leave on that note and hope that you all get to have more conversations and explore this space. Thank you both very, very much. Ask fellow participants to join me in a round of virtual applause and hearts and anything that strikes your fancy. Thank you both very, very much for your time. Really, really appreciate it. Thank you for doing what you're doing. Very grateful. Great to have you so much, everyone.
Thank you.